The 3-hour limit for determining continuous load stems from concerns about excessive fatigue and strain on muscles and joints, potentially leading to injuries. Early 20th century research indicated that muscles subjected to continuous loads for periods exceeding 3 hours experienced reduced strength and endurance. Consequently, the 3-hour limit was established as a conservative guideline to mitigate the risk of work-related musculoskeletal disorders. This duration was deemed a reasonable compromise between allowing sufficient work time and preventing undue physical stress. The concept of continuous load is crucial in various fields, including electrical engineering, mechanical engineering, and occupational safety. In electrical engineering, a continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. This definition is essential for proper circuit breaker and conductor sizing, ensuring the electrical system can handle the sustained load without overheating or failing. The National Electrical Code, or NEC, provides specific guidelines for directing conductors and overcurrent protection devices based on whether a load is considered continuous or non-continuous. Firstly, understanding the NEC definition of continuous load is critical for safe electrical installations. Secondly, failing to properly account for continuous loads can lead to undersized wiring and breakers, increasing the risk of fire and equipment damage. Thirdly, the 3-hour rule is not arbitrary but is based on engineering principles and safety standards. In mechanical engineering, continuous load refers to a sustained force or stress applied to a structure or component over an extended period. The 3-hour duration serves as a benchmark for assessing the long-term effects of the load on the material's integrity and performance. Creep, fatigue, and deformation are common concerns when dealing with continuous loads, and engineers must carefully consider these factors in their designs. Firstly, continuous loads can cause gradual deformation or creep in materials, potentially leading to structural failure. Secondly, the fatigue life of a component subjected to continuous loading is significantly reduced compared to intermittent loading. Thirdly, proper material selection and design considerations are essential to withstand the effects of continuous loads. From an occupational safety perspective, the 3-hour limit aligns with ergonomic principles aimed at minimizing the risk of musculoskeletal disorders. Repetitive motions, sustained postures, and prolonged exertion can all contribute to cumulative trauma injuries. The 3-hour guideline encourages employers to implement work practices and breaks that allow workers to recover from physical demands. Firstly, the 3-hour rule is not a rigid limit, but rather a guideline that should be adapted to the specific task and individual capabilities. Secondly, regular breaks, job rotation, and ergonomic assessments are crucial for preventing work-related musculoskeletal disorders. Thirdly, worker training and education on proper lifting techniques and posture can significantly reduce the risk of injury. It's important to note that the 3-hour limit is not universally applied across all industries and regulations. Some standards may use different time frames or criteria for defining continuous load. However, the underlying principle remains the same to prevent excessive strain and fatigue that can lead to injuries or equipment failure. The determination of whether a load is continuous often involves a combination of factors, including the duration of the load, the magnitude of the load, and the frequency of interruptions. In electrical applications, the NEC specifies that a load is considered continuous if it operates at its maximum current for 3 hours or more. This definition is critical for sizing conductors and overcurrent protection devices to ensure the safe and reliable operation of electrical systems. When calculating the required ampacity of conductors for continuous loads, the NEC requires that the conductors be rated to carry at least 125% of the continuous load current. This directing factor compensates for the heat generated by the continuous load and prevents the conductors from overheating. Similarly, overcurrent protection devices, such as circuit breakers and fuses, must be sized to protect the conductors from overload and short-circuit conditions. The NEC provides specific guidelines for sizing overcurrent protection devices for continuous loads, taking into account the directing factors for the conductors. In mechanical applications, the assessment of continuous load often involves finite element analysis, or FEA, and other simulation techniques. These tools allow engineers to predict the stress and strain distribution within a structure under sustained loading conditions. FEA can also be used to evaluate the creep and fatigue behavior of materials, helping engineers to select appropriate materials and design robust components. The 3IO limit serves as a benchmark for these simulations, providing a timeframe for assessing the long-term effects of the load. In ergonomic assessments, the 3IO limit is used as a guideline for evaluating the risk of musculoskeletal disorders associated with repetitive tasks and sustained postures. Ergonomists use various tools and techniques such as the Rapid Upper Limb Assessment, or RULA, and the OVACO Working Posture Analyzing System, or OAS, to assess the physical demands of jobs and identify potential risk factors. These assessments often involve observing workers performing their tasks and measuring factors such as force, exertion, posture, and repetition. The 3IO limit helps to focus attention on tasks that involve sustained effort or awkward postures for extended periods. Employers can use the information from ergonomic assessments to implement changes to the work environment, such as adjusting workstation heights, providing ergonomic tools, and implementing job rotation schedules. These changes can help to reduce the risk of musculoskeletal disorders and improve worker comfort and productivity. In addition to the 3IO limit, other factors can influence the risk of injury or equipment failure associated with continuous loads. These factors include the ambient temperature, the humidity, the vibration, and the presence of corrosive substances. For example, high ambient temperatures can increase the heat generated by electrical conductors, requiring further derriting of the conductors and overcurrent protection devices. Similarly, vibration can accelerate the fatigue of mechanical components, reducing their lifespan. When assessing continuous loads, it is important to consider all of these factors to ensure the safety and reliability of the system. A 3IO limit is a valuable guideline for assessing continuous loads in various fields. However, it is important to remember that this limit is not a rigid rule, but rather a benchmark that should be adapted to the specific application and environment. By considering all of the relevant factors, engineers and safety professionals can ensure that systems are designed and operated safely and reliably. Furthermore, in the context of electrical systems, the NEC provides specific guidance on the application of the 3IO rule for continuous loads. Section 210.19(1). A1 addresses branch circuit conductor sizing for continuous loads, mandating that the conductors have an ampacity not less than 125% of the continuous load plus the non-continuous load. Section 215.2. A1 provides similar guidelines for feeder conductors. Section 210.20 addresses overcurrent protection, stating that where branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, the rating of the overcurrent device shall not be less than the non-continuous load plus 125% of the continuous load. These NEC provisions ensure that electrical systems are designed to handle continuous loads safely, preventing overheating and potential fire hazards. Beyond electrical systems, the concept of continuous load extends to other engineering disciplines. In structural engineering, for instance, the sustained application of weight or pressure on a building or bridge can be considered a continuous load. Engineers must account for the long-term effects of such loads, including creep and fatigue, to ensure the structural integrity of the infrastructure. In mechanical engineering, continuous loads can arise in machinery and equipment that operate for extended periods. The bearings, gears, and other components of such equipment are subjected to constant stress, and engineers must select materials and designs that can withstand these loads without failure. From an ergonomic standpoint, the 3IO rule is closely tied to the principles of work rest cycles. Prolonged periods of physical exertion or sustained postures can lead to muscle fatigue and musculoskeletal disorders. Implementing work rest cycles, where workers alternate between periods of activity and rest, can help to mitigate these risks. The 3IO rule provides a framework for designing effective work rest cycles, ensuring that workers have sufficient time to recover from physical demands. Moreover, the 3IO rule is not a static concept but has evolved over time as new research and technologies have emerged. Advances in materials science, biomechanics, and ergonomics have provided a deeper understanding of the effects of continuous loads on the human body and engineered systems. This knowledge has led to refinements in design standards and safety guidelines, ensuring that they remain relevant and effective. Ultimately, a 3IO rule for continuous loads is a practical guideline that helps to prevent injuries, equipment failures, and other adverse outcomes. By understanding the rationale behind this rule and its application in various fields, engineers, safety professionals, and workers can contribute to creating safer and more efficient workplaces and infrastructure. In practical applications, the interpretation of continuous load can sometimes be subjective and require engineering judgment. Factors such as the specific characteristics of the load, the operating environment, and the potential consequences of failure must be considered. For instance, a lighting system that operates continuously for 4 hours may be considered a continuous load, while a motor that cycles on and off for 3 hours may not. The key is to assess the overall impact of the load in the system or component in question. In addition to the 3IO rule, other factors can influence the design and operation of systems subjected to continuous loads. These factors include the duty cycle, the ambient temperature, the altitude, and the presence of vibration or corrosive substances. For example, a motor that operates at a high duty cycle, meaning it is on for a large percentage of the time, will generate more heat and require more cooling than a motor that operates at a low duty cycle. Similarly, systems operating at high altitudes will experience reduced air density, which could affect cooling efficiency. In the context of electrical systems, the NEC provides detailed guidance on the directing of conductors and overcurrent protection devices based on these factors. Understanding and applying these directing factors is essential for ensuring the safe and reliable operation of electrical systems. Furthermore, the 3IO rule is not intended to be a substitute for thorough engineering analysis and design. It is a guideline that should be used in conjunction with other engineering principles and practices. For example, when designing a structure to withstand continuous loads, engineers must consider the material properties, the geometry of the structure, and the potential for creep and fatigue. Similarly, when designing a machine to operate continuously, engineers must consider the lubrication, cooling, and wear characteristics of the components. In conclusion, the 3IO rule for continuous loads is a valuable tool for engineers, safety professionals, and workers. By understanding the rationale behind this rule and its application in various fields, we can create safer, more efficient, and more reliable systems. The 3IO rule serves as a critical benchmark in electrical engineering, mechanical engineering, and occupational safety, helping to mitigate risks associated with sustained loads and preventing injuries or equipment failure. Understanding the NEC guidelines for continuous loads is essential for electrical safety.